So today, as the first session, we're going to hear about Radare. This is a reversing framework that has been gaining an immense amount of traction over the past few years. It even managed to get itself onto Mr. Robot. I hope you guys saw that series, it's great. It has a reputation, however, of being kind of fiddly and difficult and just hard to use, which I think is unjustified personally. But to dispel all of these myths, we have the author himself, Sergey Alvarez, also known as Pancake, also known as Trophée. And he's going to tell us all about it. And please give him a really warm welcome.
Hello. My talk is about demystifying Radare. I will try to explain a little bit what's Radare and what are the reasons behind this title. As he already presented me, I'm Sergi Alvarez. My nickname, other people in the internet knows me as Pancake. I'm actually working at NowSecure. I'm doing research and development on mobile security. And I'm the author of Radare1 and Radare2. And also many other tools like ESIL, Balabind, and all of them open source. I've been working in many things. I've been messing with Bluetooth. I've been coding assembly for video codecs optimizations, doing IoT firmware development. I've been also participating in CTF at DEF CON in the Sexy Pandas team. And also, I've been doing forensics, working as a sysadmin. And I'm mainly doing stuff at low-level C, but also I manage to do things in the website. What's Radare? Well, it's an open source reverse engineering framework. I try to focus on being portable, extensible, and expressive. It's a hobby project. I don't really get money out of this. It's something that I started just because I had some personal needs. I had to recover some files from a hard drive. And I decided to, at the time I was working as a forensic analyst, and I decided to implement a simple XML editor for looking for some patterns and dumping the results. After this, I started doing some crack me, so I decided to implement the disassembler, the debugger, etc. And I was extending the tool for every time that I needed something. I made a full rewrite 3 years later, mainly because it was like a big blob, and I decided to make it more modular, implementing different libraries and supporting different scripting languages in a better way, instead of just launching the interpreter from inside the project, just exposing the APIs and allowing other libraries to use the project itself. There was really few contributors until 3 years ago. That's something that actually there are a lot of users, many contributors. Every day I have like 3-5 pull requests to review and merge. There are like 500 users in Telegram and IRC. There are more than 5,000 users following in Twitter. And this year I organized the first Congress about the tool in Barcelona. And this is the third year that we are organizing the Assembler of Code competition. So the project is really active, and there are so many people behind. What's Radare? The name stands for Raw Data Recovery. The reason is because I started the project as something for forensics, not something for static analysis or debugging, anything like that. So it comes with an XML editor, which is the basic functionality, but also supports assembling and disassembling. There are different backends for this. You can implement new plugins for each of these functionalities. It supports a lot of file formats. Mainly, if they are broken, they are also supported. We try to fuzz every single file format in order to find bugs in our parsers. So it's pretty safe right now. It supports mainly static analysis, but there are also capabilities for doing dynamic analysis. It's also able to do hash checksums, compute entropy, and look for differences between different files. It's able to debug. It also comes with an emulator, and there are APIs for writing plugins to extend with other emulators like Unicorn and things like that. It also comes with functionalities for exploiting, like Rob Gadgets Finder, payload generator, deversion patterns, etc. It supports scripting, and there is like a package manager, because actually there are so many extensions and plugins that people use, and I don't want to bring them all together inside the core. So it's better if I can just provide a simple way for other people to install these plugins. What can you inspect? Well, this is some examples about things that people is already messing up with Radare. There is Pokemon ROMs for Game Boy, Street Fighter, same for iWedge, DNA sequencers, the Apollo 11 CPU, etc. But wait, don't lose the rail. We try to focus on myth, so we should explain a little bit which myths people think about this project. Many people think that this Radare is not stable. Other people think that it's difficult. There are so many commands. They are difficult and hard to remember. Other people think that it's buggy. It's not able to decompile. The debugger is broken. There are so many complaints like this. But first, let's try to make a poll. How many of you know this tool? OK. I guess that everybody checked the website before coming into the talk. Now, how many of you already use the tool? Half of the attendees. That's pretty good. OK, so let's talk about the first myth, which is it's difficult. This is a graph about the learning curve, starting from the point that you start opening a file and the point that you start doing something useful with it. In fact, it's pretty hard to learn this and use this tool, but you can compare this learning curve to other projects like JIT, Beam, Perl, etc. The reason behind this is because there are so many commands, but there is a logic behind them. So if you understand the logic, it's pretty easy to start learning and testing things for your own. So if you understand the logic behind them, you can create more specific commands. So you can mix different commands and create new functionality with it. You can easily hack into the code. It's pretty easy to find the place that you want to modify and just change anything in there. You can create plugins. You can write any script in any scripting language for extending the functionality or just creating a specific analysis for your target. And you can also build tools on top of it. So it's pretty easy to hack on top of this. But let's focus on the difficult part, the comments. Comments are mnemonic comments. This means that they are constructed by letters. Each letter means something, and they are structured in a way that the first letter means what's the reason for the comment. Like, for example, the letter P means that it's for printing. The second letter means that what do you want to print? So you want to print in xdump, you want to print a disassemble, you want to print a octal, etc. It has a lot of Unix-like concepts behind this shell. So you can use pipes, you can use redirects, there is an internal grep, you can also less, you can indent JSON. And all these things comes inside the tool. You can also pipe to the shell. But the reason for this is because you can just ship the Radare2 binary and in any target device, and you will have like a full Unix shell in there, more or less. You don't really need to ship a less command. You don't really need to ship other tools like JSON, PP, etc. And it tries to be orthogonal. This means that you can mix different commands and get new functionality out of there. So let's make a quick demo about understanding which commands are the basic ones. You only need to remember 5 commands. After this, you can start learning other modifiers or commands that can be helpful for your targets. But the 5 basic commands are these. We can open the file. We can seek any place. Can you read I can make it bigger. We can seek, for example, to this address. We can print disassemble of this address. We can seek back. As you see, all the subcommands are in the help. So you can just append a question mark at the end of the comment, and you get the help of the subcommands. And you can also make relative 6 like this. The other command is the P, which is for printing. We can print in different formats. You can print an examp. You can print a disassemble. You can print just instructions. And then the other command is the B, which is for writing. I will enable the catch because I don't have. I didn't open the file for writing. So if I want to write something here, I will have to enable the catch. So I can patch, for example, the first instruction, and we will see that the knob appears in there. So the B command allows you to write things in there. You can write expers, you can write assembly, you can write the contents of a file into the current SIG, etc. And then the last command, and not for this less important, is the Q for quitting the program. We can see that there are some modifiers here. We can use, for example, if we are disassembling like this, we can grep. We can also grep for some specific strings. We can just grep for the calls. We can also count the number of calls that are here. And if there is like a huge or a long list of things, we can first ask if you want to print all these things. But you can also use dot, which means internal less, and you will get like scrolling in there. So that's more or less the first logic behind all these comments. We'll learn more comments after this. Radare2 is structured into different modules. There is a libre directory, which contains all the different modules. There are libraries. We can see them in here. There is like a core, which links against all the other libraries. And each other library, it's linking against other ones. And rutil is the basic library on top of libc. So if you want to port to any other platform, you just usually need to patch on the non-portable parts, which usually is the debug that takes all the core functionalities for debugging for the specific platform. But you can also build without debugging, so it's easy to port. And this is more or less the structure of all the libraries. And each of these libraries allows you to create plugins out of them. They are under the P directory. And there is also the bin.r directory, which contains all the binaries. So we can check this. And we can also see this into the libre. So we see all the different modules in there. OK, there is another myth, which is that it's useless for forensics. In fact, it was the first aim of the project. So there are some functionalities, and there are strong points for doing forensic on this. But there are obviously other tools which only focus on forensics, which is probably better for doing forensics. But you can do many things with it. Like, for example, opening these devices, you can open a /dep/SDA or a Windows device. You can also open the physical RAM device if it's supported by the kernel. There is also an R2K module, which works on Linux and Windows and allows you to read physical and virtual memory from the kernel. It's a kernel module, and you can interact with it. You can find port for patterns and doom the results. You can mount file systems, and it's also able to understand the partition systems. This code was ripped from group, so I also fixed a bunch of bugs in group. It's also able to carve for known file formats. You can show structures and understand and parse, include files in order to show the contents of a specific memory dump with a formatted memory. It's also able to compute incremental and per block checksums. So this is handy because if you want to compute the checksums like MD5 every megabyte on a gigabyte file, you will get a file with all this, and you can also compare this with another dump and then identify which part of this file have modified. You can change the plugins for the I/O. I mean, as I said before, all the input and output is pluggable, so you can create plugins for anything. And there are plugins like, for example, gzip and EWF for loading in-case images. You can get a list of all the I/O plugins with this command. And this is more or less the list of plugins that can be used for opening local or remote targets. The uppercase -L flag can be used with Radare2, which is handy for getting the list of assembly and disassemble plugins. And the same thing goes for Rabin2, that gets the list of plugins for binary formats that are supported by the project. OK, so let's go for the first demo. OK, so we have a file which seems like it's trash. I mean, there is nothing like interesting here. We can see the entropy computation here. And there is like pretty huge. There is some zeros in there. But more or less, the entropy is pretty high. So what we'll do here is just look for known file format using the /m, which looks for magic. And looks like it found something in this offset. So we'll seek in there. And we will write the file. This created a new file, which the contents are starting at the current offset. So we can open it. And we see that this is a gzip. So we have to open it with gzip. And now we see something in there. We can use PM again, and you will see that this is a fat file format. So we'll use the m command in order to mount this partition. Using the m command, we'll specify that we want to mount this in the root using the fat file format and the offset 0. We can specify a different offset if we want to mount a different offset inside the file. Now you can use the ms with each shell inside the mount file format. And we can see the contents of this file format. We can show the contents. We can see like what's in /bin. We can get this file, and then we can just open it and see that this is a Linux ELF common ls program. So there is a bunch of functionalities that can be handy for N6. Another complaint is that analysis is slow. It's true that analysis is a really slow operation. It's blocking, mainly because it takes some time, and you need to grab all the information before doing anything useful. You can do this analysis in background, but it will still take a lot of time. And doing it in background means that you have to put a lot of mutex on the logic of the analysis, so it will slow down a little bit. And it doesn't work really well for big binaries, mainly because it takes a lot of memory and CPU time. It's sometimes not able to find all the functions. And there is the rule of adding more a's at the end of a. So if you use the AA command like this, you use AA, you will analyze all the symbols. If you add another A, you will do more analysis, and you add more A's, you will get more things. So people at the end start adding more A's in order to get more analysis, and this is probably not the best way for making analysis. So there are so many commands and configuration options for doing this, and there is this blog post that I wrote explaining some of them. So if you're interested, you can just read it or just ping me a little bit, and I will try to help you. But the idea behind this is not waiting a lot of time in order to finish the analysis and start doing something, because if the analysis takes a lot of time, means that after doing it, it will be really slow in operation. So you will have to think another more strict way for solving the problem. So what I usually do is that 90% of the problems that I try to solve, at least from my daily problems, is that I can just analyze 10% or part of the program and grab the information that I really need, and instead of analyzing the whole binary. Usually, you just look for a string, you look for references to this string, you look the functions that are using these references, and then you start analyzing just 5, 10 functions. And after this, you don't really need much more information. So you can just use the comments for analyzing the target information that you want. You can analyze much faster because it's much less content. And yeah, we are improving on every release. So if you're updating frequently, you will get fixes and faster analysis on every build. Well, you have to understand the logic behind all these comments and options, and we will see some of them. So this is the first demo. I will open a hello world in Go. If we make like a full analysis of all the symbols, because Go binaries are pretty huge, because they statically link all the libraries and symbols, etc. So it took, well, we can compute this like with this prefix. This is like time in the bash. So it took like 8 seconds. And after this, we can seek to the string. So we see that the hello world is in here, and we see that data reference in there. So we can just seek to the reference, and we see that the hello world string is referenced in this instruction. But it took some time. I mean, it was 8 seconds. I mean, this is a simple example, but if you try to do this in a huge, bigger binary, it will take more time. So let's do the same using this script. This script basically looks for the hello string. It seeks to this address, and then, well, it renames the flag. It defines that this is a string. It changes the block size for speeding up the search, and then look for references to this offset. If we run this script, it took only 2 seconds, almost 3. And it has identified the same offset and the printf of the instruction. So as you can see, you can speed up a lot the analysis. This is a simple example, but it can be there is much more difference if you try to in a big binary. Another thing for analysis is that sometimes the references are not that clear. This is a hello world for iOS in ARM64. And we can seek to the hello world string. And we see that there is no reference because we didn't analyze anything. So we will make like all the analysis options. And we see that there is a data reference in here. But if we try to analyze like in a simple way, we'll see that there is no reference. The reason behind this is because in ARM and also other architectures, the references are computed in more than one instruction. So you need to emulation in order to understand the correct reference out of the. So if we go to the main, we will see that the printf is getting the address of this symbol in here. So it's getting the base address and then assuming an offset. And we can enable the emulation. And using the emulation, you will see that every instruction is getting emulated, and then we get the values of the registers on each instruction. So after this, we will see that it's creating in ADRP, it's getting the reference to the string section, and it's incrementing the offset to get the hello world string. So there is a command AAE, which is analyzing using emulation. And depending on the architectures, for example, in MIPS, it's really handy. There is other ways for getting references using AAB, which looks for pointers to data or strings or known pointers inside the same address space. Yeah, you can see that there are so many comments under the AA and AA subcomments. Okay. Another complaint is that Radare is not documented. And well, that's not true. It's documented in C. And there is inline help in every comment. You can get inline help without having to get to any browser or any book in front of you. There is also a book that I wrote for Radare1, and Meijin updated it for Radare2. And there are already a lot of talks, slides, blog posts, and YouTube tutorials for understanding how to solve some crack myths and things like that. So it's not really true. It's true that it's complex, and sometimes it's hard to find the help for something, but there is a IRC and Telegram channels that you can ask in there, and you will get help pretty quickly. Let's talk about the compilation. Radare2 is not able to decompile. It's able to do things that are similar to the compilation, but that's not really the strength of the tool, because it's hard. The compilation is not something easy. So we try to delegate this to third-party tools. Niterman wrote the plugin for Radare, which is an online service for decompilation. It's basically a plugin written in Node.js that uploads the binary that you're analyzing to their servers, and you get an API for getting the disassembly of the decompilation of different functions that you are analyzing with Radare. So you get comments and the C code, C-like code into the Radare shell. There is also the project Radare2, which is a Rust implementation of the compiler, which is pretty academic, and it's not yet usable. I mean, it's work in progress, and there are some starting of the project, but it's not really solving any real-world problems yet. I hope that maybe in 1 year or 2, it will be an option. There is also Boomerang, which was supported in Radare1. I think that Boomerang right now is not really maintained, so there is not much interest in supporting it in Radare2. But it will be pretty easy to port the scripts from Radare1 to Radare2. And last week, I ported the Snowman, the compiler. This is much more updated, and it supports ARM and x86 for 32 and 64 bits. We can make like a quick demo for this. Oops. Yeah. We'll try to come back to the after it's compiled. So let's talk about the disassembly. Disassembly is probably one of the good points of Radare, because there are so many options for disassembling. You can colorize the instructions depending on the type of instruction, which is pretty handy for reading code, because you can easily identify where are the jams, where are the mathematical points, where are the parts of the code that are doing crypto or doing like traps or some syscalls, etc. There is also support for analyzing variables and arguments, so you can identify where these variables are accessed in the disassembly. There is also support for pseudo disassembly. This means that it will parse things like at EAX, 3 and convert it to something more human-friendly, like the expression at the right. And this is handy sometimes when you want to get some more C-like code, but it's not really a way to decompile. OK, so we get the R2 now in there. Yeah. OK, too bad. Let's talk about the disassembly. It was working yesterday. So as you can see, there is the disassembly that you can. It's highlighting the instructions in different colors. You can change the color scheme. You can also enable the pseudo-disasm. So you get things like this. And the thing is that there is PDS, which shows a summary of the disassembly of the function. If you analyze the function and you get the PDS, you will see all the references of C strings and calls of this function. So you can read like a summary of what the function is doing. You can also use PDC, which is a pseudo decompilation, which is using the ASM pseudo and doing some logic of basic blocks in order to nest the different blocks. And you can put the comments at the right, put them at the bottom, etc. And there is all these things are interactive in visual mode. So if you press uppercase V, you get this, and you can scroll around, see where the destination of the jump is going on, etc. And yeah, finally, there is a nasty art graph for all the functions, so you can get analysis. You can also, if you are in this basic block and you want to fold it, you can also fold them. You can switch to this assembly and you are moving back to the same point that you are in the graph, or going back to here. So there is no user interface, but command line is pretty handy. Another complaint is about stability. People say that Radare2 is not stable. The main reason for this is because they are using an old version of it, because they are not using the JIT or the last releases. And we can talk about the stability depending on the amount of crashes that the user is experiencing and the amount of changes in the comments and the APIs. Right now, we are after 1.0, so I try to put some stability on top of this. The comments are pretty stable. Most of them are already used for many people, and they are quite clear, so this is not going to change. The APIs are quite stable. We try to refactor all the time. It's a project that, I don't really care about breaking something that was wrongly designed in the past, so I don't want to keep compatibility for years for something that was wrong at some point. So C API can change, but it's quite stable, so you can still do things like that. And if you want to pass the output of a command, you can just append a J letter at the end of the command, and you will get the JSON output. So you can do things like this. If you press the I letter, you will get the information about the header of the binary. You can get the symbols. You can get the sections. You can also get the sections like this. And the thing is that if you append a J at the end, you get this JSON, which can be indented using this. And you get the indentation in the JSON. This is pretty easy to parse because all the programming languages, the modern programming languages, have libraries or they support parsing JSON to native objects of the language directly. So it's pretty handy for scripting. And the thing is that this is much faster than using FFI or trying to deserialize all the binary structures from C into Python or any other language, because it's allocating a lot of objects in a non-properly way, because parsing JSON parsers are much faster than any other parser right now. So our complaint is that some specific functionality is broken. Many complaints, or most of the complaints that I receive every day in IRC are already fixed in JIT, so please update your version of Radare2. If anybody reports a security bug or any crash is found, they are fixed in less than 1 day, usually in less than 1-2, depends on how far the laptop is from me. I try to follow the rule of you see it, you fix it. So if you see a problem, I try to teach you how to fix it before just saying, it's broken, and I try to fix it later. This is because the community grew too much, and I try to teach the community to be self-aware of the problems and how to solve them, and how to report properly, and how to just report a reproducer, say at least pass the backtrace or something that can be useful for me to understand what the problem is. And mainly, you should also post the version of Radare that you are using to see that if it's not the last version, I will not fix it, because I'm only fixing bugs that are already in JIT. So we try to make a release every 6 weeks. This is something that I decided after seeing how the Rust project works. I think that 6 weeks is pretty nice time schedule, mainly because having like 1 month is really predictive. I mean, you expect like the first day of every month to update something, and every 6 weeks it's something more random. So at the end, I'm rounding up, down, and you never really know when the next release will be. So that's kind of surprise and funny. And the thing is that if you release, some years ago I was releasing once or twice a year, and this was not really good for the project, mainly because if you are releasing too few every, there was like 2,000 commits to review. There is a lot of things to test. There was no test suite at the time. And well, right now this is solved by making shorter time releases. So we have a test suite and we test everything more frequently. So it's hard to make a JIT clone and get a version that Radare2 is not working. But there is also the problem of Debian. Debian is a distribution that tries to be stable, and by stability they mean that they are not updating really frequently. Well, the thing is that the current version of Debian stable is 5 years old. And if you can imagine that every 6 weeks there is like 400 commits, you can see how many commits are in 5 years. So I would recommend you to not use the packages from Debian. There is packages that are already shipped in my repos, and you can also use the packages from SID, which are a little bit more updated, but they're still old. So as I said before, I tried to use the test suite. I used the RDD pattern, which was invented by me, and it's mainly a regression development pattern. And the thing is that after you find a regression, you write a test, and then you test that this regression will not happen again. The reason for this is because it's too late for doing TDD. TDD is test development, and this means that you write the test before writing the code. So as long as the code is already there, I have to write the test after this. And as long as we are doing continuous refactoring of everything in order to improve the stability and portability and the reliability of the code, some bugs can reappear. So it's important to test everything. Right now, the test suite takes like 15 minutes to run on Travis, and half an hour for OS X. And it's too slow for Aperture, so the Windows test suite is not running yet. We try to impose the fuzzing inside the development process. So before any release or during the development of every release, there is some people doing fuzzing on different file formats, the command line shell, different inputs into the program. And we use different tools like Valgrind, Sun, CLang Analyzer, and Scan Coverity in order to identify which are the parts of which are more buggy and which ones are the places to solve the bugs. This is important mainly because there are so many contributions. Many of them are from people that are starting to code. And we try to follow some standards. So there is some coding style, and this requires some education to the community. Another complaint is that this is not written in Python. I know that C is not the perfect language. It's easy to make mistakes, but Python is not the solution. I mean, maybe at some point there will be a language that can replace C, maybe Rust, or maybe Swift, or I don't know. But maybe Rust is the one that fits better inside the philosophy of the project. But if you want to use Python, there are 3 different bindings for the native APIs. There are 2 different bindings for R2Pipe supporting different transports. I will explain later what it's R2Pipe. And you can write plugins for EO, Urbin, and Rasmin in Python already. The reason for not choosing a dynamic language for this is because statically typed language allows you to catch errors at compile time. So it's easier to identify problems before running the program. There are so many tools available in order to profile the bug and optimize or port to different platforms. It's faster, it's native, it's a smaller footprint. There is not really a runtime library that ships inside the final binary, so you can easily put and statically link it and put it in a router or any other device. And C also transpiles to JavaScript, so you can run Radare in the web browser. And that's fine for me, at least for the 90% of the problems. And for the rest, you can just use any scripting language. OK, let's talk about the graphical user interfaces. The main complaint is that there is no graphical interface, but that's not true. Terminals are scary. People are scared about the terminals. And they used to like to use the mouse and try to click and do things like that. So the real problem for Radare2 is not that there is no GUI. The problem is that there are so many of them. There is a visual mode. There is a tiled visual mode, which is DWM-like. There is different web user interfaces. One of them is this, which is material-like, and this is the default for Android. There is the other one, which is done in jQuery mobile, and it's more desktop-friendly. I also brought the Blazor, which is Node.js and Cursor-like interface with Windows and things like that. I also brought Radare, which was written by Radare1. And this is basically a BTE terminal with a GTK interface that there are some buttons and menus that you can just, instead of typing comments, you can just run the comments from the menu. There was a complete interface written in Bala, and it was working pretty fast and pretty nice, but it was abandoned because it was boring to write graphical interfaces, and I think that nobody cares about that. So I never released it, but it's there. There is also Boken, which is a Python GTK interface that it's right now not really maintained. I think it's working in the last version of Radare2, but it's not adding new functionalities, and it's just for static analysis. Now there is a guy, Mandingo, who is writing a new user interface in .NET, but he's focusing on Windows. So the thing is that the dependencies of this project are depending on the Explorer widget and also the MFSC API. So it doesn't really work on Linux or OS X. So it's not portable. Maybe someday it will be portable. 3 days ago, a guy made a mention to me in Twitter, so I had to add this slide. And he's writing a Qt5 interface. You can see a screenshot here, right from the GitHub. But let's talk about a real user interface. The author of Boken, Hugo Teso, has been working for a year and a half, something like that, in a new user interface written in Qt and C++, which looks like this. This is the main user interface. It supports actually only static analysis, but it will support debugging and emulation, other things like that. And it will be released early next year. OK, so let's talk about scripting. It's a topic that it's complicated. Really, if you focus on the problem, you only need to understand the comments, and you only need to understand all the APIs. So if you know how to use Radare, you can script Radare pretty easily. Mainly because I was trying to follow different paradigms, like trying to make the bindings more language-friendly. So at the end, you really need to have bindings specific for each language. And the reason is that this is too much work, and APIs are changing. So at the end, I wrote a tool, which is Balabind, which transpiles BAPI interface into different interfaces for different languages. So I create a single file that interfaces the C code, and it creates Python, Perl, Node.js, etc. bindings for all these targets. But this was not really stable at all, because there are some memory problems because sometimes it's hard to manage the references and things like that. So at the end, I got the idea of implementing R2 pipe, which is basically a pipe on top of these 4 comments. The API provides an open method, which allows you to open using a specific transport to open a target file. And then you have the CMD command, which basically runs a command in Radare2, and then you get back the result. And there is the same with the JSON output, which basically returns a native object of the result. And then there is quit. So it's just only one comment, only one method that you have to remember for using this API. Let's make a quick demo for this. This is a script for getting the configuration file of the Mirai malware. This is a botnet. And this is the script. It's written in Python, and it's using R2 pipe. It's basically extracting the configuration file out of the binary. You can use it like from Python, like doing it like this. And you get the config file in there. You can also use it from inside Radare, so you can just connect it like this. Or inside the shell. So if you are inside the shell, you can interpret the file just using the dot. So it's importing the file and running it. There are so many examples in many different programming languages. In fact, this is the list of all the languages that are supported for R2 pipe. Not all of them support all the transports. By transports, I mean that you can use R2 pipe through HTTP. You can also use it through TCP. You can also use it with pipes, just spawning the binary and reading, writing the standard input, standard output. This works in all platforms, in Windows, Linux, OS X, and yeah, there are examples inside the directory. So if you go into the R2 pipe repository, you will see that, for example, for Node.js, there are examples in there. And you can see, for example, there is an IRC bot. There is also a syscall emulator, which is basically implementing a syscall handler in JavaScript. And you can run this hello world, which is basically this code. And this will have to install the npm. Okay. Damn. Well, I can change this. It's just a stupid thing. Yeah, anyway, the Python example, this is the same in Python. So it's running the syscall handler in there. And it's basically saying that you have to, using ESIL for emulating code, and then you get the R2 pipe script executed after this. OK, so debugger is confusing. Many people think that the debugger of Radare2 is strange, mainly because it's a low-level debugger. The main reason for this is because I don't try to replace source debuggers. There is GDB, LDB, and the Visual Studio, which are pretty good source debuggers. But Radare2 aims to work for binaries that you don't have the source code or different targets. So when you're starting the debug with Radare2, you are starting the debug into the dynamic loader of the system, not inside the entry point. The reason for this is because some file formats can exploit vulnerabilities inside the DLD and execute code before the entry point, or there can be more than one entry point. Also, there can be changes in memory that will not be applied into the disk. So some people complain that, hey, I'm patching the binary in memory and then execute the program, and the program is not patched. The reason for this is because you're patching the memory and not the binary itself. And if you want to create a specific environment, you have to use Radare2, which is a tool that comes with Radare2 that creates a profile to specify, for example, the user ID, the chroot, the different directory that you want to run as a command, all the arguments. If you want to change like a file descriptor, like standard input, you want to be a socket, it's listening a specific port, etc. This allows you to create a profile for running the program every time. This is handy if you are trying to make a crack me or things like that. So the debugger basics are like this. You can spawn, attach, you can create plugins for all these things. And there are plugins, as long as I said before, there are plugins for all these backends. So you can use a native debugger. There are more than one native debugger. There's people writing their own native debuggers for Windows and things like that. You can use attach to a GDB. You can also attach to WinDBG, Box, etc. All the subcommands of the debugger are under the D letter. And you can also do local or remote debugging, and you can inject code. There is a dx command that allows you to inject a bunch of bytes, and then it will get back the result of the state. The GDB backend is not working on the platforms, mainly because the GDB protocol is crap. It mixes binary, plain text, and XML in single and with ASCII checksums, which is a really bad decision. But and they try to re-implement the thing for every single platform. So every time that you try to connect to a new platform, you have to use different solutions for getting or writing the registers, or reading, writing memory, or doing steps and setting breakpoints and things like that. So it's kind of a hell. So it's work in progress, and right now it supports Intel mainly. So you can use it for debugging Windows or Linux kernels, attaching to QEMU or things like that. And it's work in progress for MIPS, ARM, and AVR. There is R2 LLDB, which is a project that I wrote now secure, and it's mainly an R2 pipe script that allows you to you are inside LLDB and you run this Python script, and it will allows you to attach from Radare in there, and you can use all the functionalities, read, write memory from Radare2, and just have the shell in there. This is nice because if you are working with Apple things like Apple Watch or iPhone devices, you can use Radare2 to debug binaries in there without having jailbreak. And there is also R2 Frida. Frida is a dynamic tracer that injects a library which contains a JavaScript interpreter in there, and you can put the scripts in there or just use the core libraries for running code in there. This project is written by Ule Andre, also working in my company. And it allows you to, it works in many platforms, can be used in OS X, iOS, Linux, Android, Unix, Windows, and it's pretty fast. I mean, maybe thinking about JavaScript and all these things make you think that it's slow, but it's really fast. And it allows you to make introspection inside the process, so you can do debugging inside the process. Let's make a really fast demo. So I have Node.js running in this terminal, and I have Radare2 in the other one. And I will use Frida to attach to this process. Right now, we can get information using the \. And we can see the list of commands from the Frida plugin. From here, we can get information from the binary. We can get information from the exports, for example, the symbol that... Ah! You can write memory from the touched process. You can modify it or do whatever with it. You can also analyze it and get the graphs out of there. Yeah, if this should work. OK, it's not. OK, so what I'm going to do now is use the DTF command, which allows you to trace a specific symbol, and use a format string for tracing this function. So now, every time that the Node.js process is writing, using the write symbol, it will print something in there. We can also use show the backtrace, inject JavaScript scripts in there, etc. OK, let's talk about the ESIL. ESIL is the virtual machine that comes inside Radare2. It's an intermediate language that basically it's translating every instruction into a string. We can see this in there. So if you press uppercase O, you will see a string. And this string represents what the instruction is doing behind the scenes. So it's a fourth-like language. It has two different stacks. And it's text-based. The reason for this is that you can easily read and modify what the instruction is doing. You can also change the instruction in itself. So without having to recompile Radare2, you can change the expression. And this is used for many things, not just for emulation. It's used for analysis. It's also used for assisted debugging. So if you want to specify a specific string, like defining, I want to continue this execution until a specific register have a value that is in this range, or you want to identify if the specific jump is going to be executed or not, or find references, such expressions that are matching some memory. Like, for example, I want to find a specific region of memory that contains some D word and then some 0, etc. You can use ESIL for this. These are some of the commands that can be used for emulation. It's basically the same for the debug, but using AE as prefix instead of D. And there is also support for Unicorn, but it's not as complete as the ESIL one. So here is a crack.me. It can be solved using this script. It can be solved using this R2 pipes, this R2 script, which is basically seeking to a symbol that you want to emulate, running the code in there, and stopping at the point that is comparing the two strings, and then dumping the register values. So we do like this. You get the password. And the same thing goes for the Python. So it's basically doing is calling the check password function, which is in there. And then inside this function, it goes for looking for the string compare, and then getting the value of the registers. If you do this, you can see, for example, that in the debugger, you can continue the execution at the entry point, and then you can use DRR to get the... Wait, not in the debugger. So I'm continuing to the entry point, and then I'm using DRR to use telescoping in order to get information of every register and where they're pointing to. So you can also do the same in the stack to get all the pointers of the strings and so on. And many things like these are useful and used from there. OK, so about exploiting, which is the final slide. There are so many functionalities in Radare2 that can be handy for exploiting. It's like you can patch code in memory. You can do things like that. So I'm right now in the debugger. So I can just put the cursor in anywhere, and I can press uppercase A, and I can just patch the code with, for example, with this. This is handy for preparing some specific environments. There is Emulation, Debugger, static analysis, and there are some handy functionalities like generating and finding offsets of diverging patterns. You can do register telescoping, like I showed before. You can do heap analysis. This is only working on Linux, but it will be ported to OS 6 and Windows soon. And let's make a quick demo about the Radare thing, which is a front end of Radare2 written in Node.js that basically allows you to create drop gadgets. So you have all the drop gadgets at the right side. that are found in the /bin/ls binary. You can add them in there. You can also remove them. You can move them around. You can also drag and drop. And when you have all this thing ready, you can just debug. And you get the terminal ready for debugging the ROP gadget that you have written. So you start inside the red. So you start stepping, and we are stepping all these ROP gadgets. Yeah. And to finish, I would like to show you one of the reasons that you can use Radare2 for extending or using a specific exploit. I'm using Dirty-Co exploit for writing an EO plugin. So this is a vulnerable Linux. It's 1 month from 1 month ago. I don't know if you know the Dirty-Co vulnerability, but it's pretty funny. And you can read more in these URLs. What this vulnerability allows you to do is to modify files that are not owned by you. So you can modify, for example, the etc services. I don't have permissions for this. But if I'm using the Dirty-Co plugin, I can see this, but if I write some string, you see that it's not changing. The reason for this is because this exploit is a race condition, so I have to write several times in there. So I can just tell Radare2 to write this comment 10 times, and it will patch the binary. So you can just cut and get the file that have been changed. So you can use the IO plugins or any other plugins for exploiting any of the bugs that are in the systems.
So I'm afraid we run out of time for questions, but Sergi said he's going to try to arrange a meeting for you guys, someone here during the Congress still. Where can they find you?
If you know any place that I can meet with our people there.
So I would suggest, I was just linking up with him on Twitter. Let's thank him again for this great series of demos and give him a round of applause again.